Alrighty. Well, thanks so much for joining me this afternoon. My name's Rob Shanks. I'm the CEO and co-founder of a company called Moog. We're based out here right in Data Center Alley in Northern Virginia. And so we are going to talk today about how we make AI and IT a little bit more circular. So it's always a little helpful to give an introduction of why I'm standing here on stage and kind of what brought me on this journey. And so for about a decade, I worked in consumer electronics manufacturing, unfortunately in a lot of places that look like this. It's not great, but it is the reality of when we think about cheap, highly available, mass-produced consumer electronics. And it was through this journey that I discovered I was contributing firsthand to the 62 million ton problem of e-waste because of how we were designing, manufacturing, and ultimately not recovering our products. And this e-waste, it accounts for the fastest growing waste stream we have today. Now, right now, we're only recycling about 22% of electronics. That number has come up. About 5 years ago, it was 17%, so we're making some progress. And I would say overall, the data industry, it's universally agreed we're doing better than this. But this accounts for kind of all electronics. But within this, there's actually about $62 billion worth of precious commodities, metals, all the valuable things that we need to produce the electronics. And so this is a great opportunity of how we use that material that's currently being lost to landfill. So 4.5 years ago, I started a company called Moog, focused on using robotics and design for circular manufacturing. And through that journey, we've been amazingly supported and work with some fantastic companies, some in the audience here today, like ABB, in how we reshape this future for circular manufacturing. So let me just start by kind of setting the stage for what circularity looks like in data centers. For those that might not be familiar, circularity is really focused on how do we keep things in the highest form of value circulating through these systems, both at an economic but an environmental level. You can think about the world that we live in today as more of a linear process, where we're extracting metals, materials from the ground, we're refining them, we're making things, and then we're discarding them. Very few things have kind of a second, third, fourth, fifth life, and that creates kind of a one-way, hyper-optimized supply chain of how we build, scale, all in kind of one direction. But how do you kind of bend that curve of that linear into something circular? And you can think about the distances of these loops in kind of more energy. So ideally, we can just reduce what we're using to build something in the first place. Second to that, how do we reuse within our own organizations, our own data centers? We then kind of take a wider loop into remanufacturing. So how do we take things back to new? And then kind of at the very end of that curve, you have things like recycling, which is more about material recovery. So you're still going to have to put quite a bit of energy to get back the base state of that material so you can build new things with it. And then, worst case is absolute waste. But what we're trying to do is eliminate all waste through these closed-loop circular systems. So how do I think about that? Well, I think the circular economy you can really define as these re-X's, like I described. It's all the way from that reuse to the remanufacturing, all the way down into things like that material recovery perspective. And so we focus on how do we make these re-X's easier, more scalable, and ultimately the default way of doing business. So why is this important? We live in a very dynamic market right now, and things like ESG and sustainability has taken a bit of a hit, a little bit of a back step. But what's interesting about the data center industry is there is a baseline necessity to recover what you have from a data security perspective. Every DC is filled with data-bearing devices, DBDs. It's a thing our customers tell us about all the time. But in those data, you have your customers' data, you have third-party data. You cannot just discard that into landfill. The liability of that loss of data, that data risk is just immense, right? So you have this baseline activity where servers are going to be decommed, they're going to be wiped, they're going to be processed just for the data security, which is a unique aspect within the data center market, which is why it's a really good kind of leader of driving circular economy. Beyond that, we have economics, really a big driver in all states of business, but certainly with data centers. It does fluctuate year to year how the hyperscalers think about their overall use. So we've gone from 3 years to 5 years to 6 years. Now with AI, we're back to 5 years. It very much depends on the hyperscaler. But ultimately, being able to extend the life of your servers in your deployed DCs can save you billions of dollars a year. That's not my numbers, my fanciful entrepreneur spirit. Those are kind of the 10K reported numbers here as we think about amortization of server equipment and extending life. Now, why is circularity kind of important to thinking about server life extension? Well, if you can harvest components from what you have and use them as critical spare parts, drive that back into your own supply chain, you can keep those things running longer and ultimately not having to decommission as quickly. And then lastly, it's that sustainability, something that's obviously near and dear to our hearts, and it really goes down to the core of that Scope 3 emissions problem, embodied carbon, all the energy that gets used to manufacture and produce these physical assets. This is kind of the really, really tricky, hairy problem that we all deal with because it's upstream, it's downstream, we're all part of the system where that material is flowing through. And what circularity does is keep that embodied carbon in the system as long as possible, ideally at its highest value, so we can all kind of amortize it out before we have to go back to ground to do the most intensive energy processes of refinement. So let's talk about some market dynamics, where again, we're in an interesting time and space. We have the kind of hyperscale ITAD providers. These are companies like Sims Lifecycle Services, Iron Mountain, SK Tess. Iron Mountain, bought a great company called IT Renew, a couple years ago. SK got into the business by buying Tesham. These are focused on kind of global contracts of how you service the hyperscalers. But additionally, we have the hyperscalers moving into this industry themselves. So the Microsofts and Amazons are spending the money, spending the infrastructure to build their own infrastructure so they can do this kind of fully vertically integrated. And that's with the Microsoft Circular Centers and then the Recycle Reverse Logistics with Amazon. So let's we all know, I think part of this conference here, what it's take to build the data centers, power the data centers. But let's look at kind of that journey of circular processing when we think about the decommissioning. What happens when you're done with your rack in your DC and when it needs to come out, and how do we create circularity in that? So typically, the DC will do a drive wipe. So they'll try and delete everything digitally off the rack whilst they're still running. They usually run that process over about a week. And then it gets picked up onto a truck and loaded in at a rack level. So we unplug power. Now, to be clear, Moog doesn't do this. I'll show you what we focus on. But ultimately, those racks go into trucks. Those trucks go to these decommissioning centers. Again, they're either kind of ITAD focused, so a third party, or in some cases, they're even co-located hyperscale owned run facilities like some of the Microsoft Circular Centers. So it's helpful, and I promised I would show you some robots. This is how the future that Moog is building and what we're working on how we create that circularity. So this is what we call a Moog microfactory. This is a deployable robotic cell that's designed to automate these re-X activities. We've designed them to be highly deployable and configurable to the different needs of how we keep these things at their highest value. We can then scale them, so start with 1, scale up to 20 in a given facility, and we're working across that whole value chain, and we're kind of talk about some of the specifics throughout this talk. But ultimately, we need to go from those racks, take out the servers, put them into these different cells, and then track and trace, and then go through this harvesting process where we go and take out all these components. And then you can see the robots can choose the different tools. They have a wide variety of different capabilities, all with the goal of dynamically processing that material for its highest economic and environmental value. You can see even we do some remanufacturing, where if we find the highest value is going to be putting some of those things back together in a remanufactured server, we could go ahead and do that. And one of the big challenges here is what's been holding back robotics is that's a very dynamic world, right? Robots are typically designed for things like automotive manufacturing. You're building the same car across big lines. End-of-life servers is a much bigger wide mix. So we need to have intelligent automation that can adapt to the material that it's processing. But let's start with some of that automated rack processing. Why is this important? Well, the servers are getting heavier. A JBOD, kind of your standard HDD server, can weigh up to 300 pounds, if not more. So that's really, really challenging for even someone with some semi-automated equipment to get those out of racks and then put them into the downstream processing. The racks themselves are getting larger and heavier, and this is only going to get much, much worse or better, depending on how you look at it, as we containerize these systems and we bring in bigger and bigger, higher power density racks. But there's some positives here. Communities like OCP, Open Compute Project, are standardizing these racks, narrowing the kind of range and diversity of racks, which makes it easier for automation. So if you look at OCP ORv3, kind of the latest of the art, you have a much more standardized process where we can all build tools around handling that. And so it's not just Moog working in automating DC. We're talking about some of the other great innovations going on. But one thing here is Meta has some fantastic tugs. They call them automated tugs, but they're actually fully autonomous carts, and tuggers that are pulling around the racks between the data centers. So this is kind of the type of automation that's needed. And then Moog, we've worked on automated de-racking. We've used robotic arms. We've also found the limitations of robotic arms. So we've recently gone from a Gen 1 system that uses robotic arms to pull out these servers into our cells that you'll see in a second, to something more bespoke that is much more capable at high diversity racks and can move these massive, 300-pound racks here. So you can see we have some very small little arms here that are going and pulling out these racks onto a conveyor belt, onto an elevator. I will say that the internal name for this project is G2E, the Great Glass Elevator. But it kind of gives you the sense that we need a general purpose, highly capable machine that can change the tools depending on the racks. And what this enables us to do is have autonomous systems that can be fed these larger microfactory installations so that we can either use robots or people to load racks into these larger constellations of microfactories. So as we dive a little bit deeper, we think about that server level processing, right? So typically we're asked to look at things like DIMMs, CPUs, GPUs, socketed components, so little flash chips, all the way down into kind of your mechanicals and various cabling. And so here is a quick video of one of our Gen 1 systems that uses some of that robotic arm loading. You'll see we load it into the work cell. This is not a conveyor-based system. It's a cell-based system, which allows us to have a more dynamic range of intra-cell processing. Not to get too process automation language on you, but it allows us to kind of do a full end-to-end job within inside a single cell. You can see it's pulling out that hard disk drive from the front. We're also scanning and using an array of cameras above to influence what the robots are doing, additionally scanning, tracking and tracing, doing visual inspection. And then we're going and putting them in the various different receptacles per that type of disposition path. So we'll dive into some of the specifics that we do on the highest value components, but you can generally think of this as a highly variable process where if we're going to recycling, we can put it in large gaylords that are going to go into material recovery processing, all the way up to high precision trays where we know exactly what chip is in what slot, and that can feed kind of downstream processes. To kind of ballpark it for you, a typical server process for us takes about 3.5 minutes. It uses 2 robotic arms, and I can attest, to some of the latest stuff on our new Gen 2 systems. They're moving scary fast. So I used to be very comfortable putting my head in these things, and now I'm very much taking a step back. But you can see we go all the way deep into things like CPU processing. Again, if customer needs some level of reassembly or what their disposition path means, we can go ahead and put stuff back. And for this specific process, that whole rack was being processed in a particular way. So we actually re-rack the whole thing. And the arms themselves can bring the different trays, receptacles, all into that system. So, it should be noted that, some of the ITADs, the hyperscalers, we have some really good processes in place, but we have some labor challenges, and I know there's been a lot of discussion on workforce development. And so how we think about that is we need to provide these workforces with better tools, because if we are the ones asking them to be the robot disassembler, they're not particularly good at it, and it's also not great work, right? So how do we 10x the output of these human workforces to kind of meet the scale of the challenge? So as we think about some of the specifics here, as we have a data center group, we can get a little bit deep and specific. So DIMMs, this is one of the high, reuse capabilities in the market today. We're in kind of DDR5 DIMM memory. Most of the stuff being decommissioned is a DDR4. But that performance trade-off, as well as cost, availability, reharvesting what you already have, is an amazing redeployment opportunity, especially at kind of the hyperscale level. So when we think about DIMMs, we're typically looking for 32, 64 kind of gig DDR4 or above, and we're harvesting those in a way that they can be reused, redeployed, requalified back into new server manufacturing. Now, if you don't have that need internally, you can resell. There's a massive, massive electronics commodity market where you can put 50 trays in a DIMM, don't even need to test them, and you can sell those kind of on the open market, and there's people that buy. It's a very fluid market. The prices go up and down, but ultimately, there's a lot of money being made here on reselling those components. And lastly, if you really have to, there's recycling paths. And so if you're in a very, very old DDR3 and there's not enough demand in the market, you can go through kind of the precious metal extraction recycling on this. But it's quite energy intensive, and ultimately you're going to get more value, ideally, and less environmental impact if you can find reuse. From a testing perspective, there's kind of two paths there, and typically we do both. You're visually inspecting them. Occasionally, very, very occasionally, you will see charring on like a NAND chip. So we run every DIMM through a visual test. We're looking for any kind of charring, any kind of deep gouges, scratches, missing components, things like that. We're also using that visual inspection to track and trace and pull the full ID from the labels. And then we put them into functional testing. Again, this is a variable process. It somewhat depends on what your internal use cases are or what the market will pay the most for. But a test can run from anything between 30 seconds to 4 minutes on a given DIMM. Now, when you think about that reuse, you really can look at it as a new procurement method for your manufacturing. How do you recover those things, hold them to the same quality of procurement as your new manufacturing? And there's some facilities that those two activities, the demanufacturing and the manufacturing, are happening in the same building. And so they're actually harvesting on one side and then tunneling material across to the manufacturing side, being put in new servers. The other path is spare parts. As you think DIMM, especially DIMM receipts, I don't know how many people are in day-to-day data centers, but it's a very, very common activity where your server is going to act up, throw a flag, and all that needs to do is you need to replace that DIMM. A lot of time it's just reseating the DIMM, but for time and efficiency, a lot of people just replace the DIMM. So how do you, again, harvest what you already have to maintain your fleets with the things that you can harvest? And then that remanufacturing just comes into how much testing, reprogramming you want to put into it. And then, in our industry, we spend a lot of time thinking about sorting. There's a lot of mix of DIMMs. DIMMs, need to be kind of for resale, put in like-to-like, same matching MPNs. So I deal a lot with trays. It's not something I expected in my life, but I spend a lot of time on the pitch of specific plastic trays and how we make robots fill those trays with millions of DIMMs. So getting into a more hotter commodity in the market, GPUs. Now, there's not a lot happening from a decommissioning side of GPUs, from things that have gone through their full life cycle. But what we are seeing is there's tremendous problems with the commissioning of GPUs. So when we're bringing up these racks, we're seeing so many failures in GPUs, and those will then need to go through kind of a break-fix process. For a $30,000 GPU on a $150,000 board, that is something that you need to handle with extreme care. The reality is here, these GPUs are being placed by robots in the factory and need to be put back on boards by robots. There's specific torque kind of placement, especially when you deal with the thermal interface material. So the human break-fix processes that we have today are not capable of really getting full reuse out of those GPUs, and we're seeing so many infancy failures when we're bringing up these new AI factories. So there's a lot to be done here, but it's an exciting kind of super high value component of the market right now. That automation is somewhat necessity when dealing with them. And then there's this other dynamic that I think is kind of new to the industry. We're seeing the hyperscalers increasingly invest in their own custom hardware, their own accelerated chips, their own proprietary IP. This, when you think about sending to a traditional ITAD, there's IP concerns. If Amazon, for instance, has an Annapurna chip, they do not want anybody else in the world to have that chip, right? So that creates a whole new disposition path that cannot be resold on the open market. Additionally, these things are some of the highest in-demand kind of components when you are thinking about building out new data centers. So how do you repurpose these custom things? And so this, I think, will, again, drive a lot of reuse, a lot of sustainability, just out of necessity of where the market is today. And then lastly, hard drives. There's hundreds of millions of hard drives that are produced a year. It is a number slowly coming down as SSDs ramp up. But it is ultimately, we think, a long-term solution to storage, given the lower cost, the lower embodied carbon. And unfortunately, the state of the art, even though they're wiped, is they are primarily shredded. And I'm sure some of you have seen them in your DCs. There are much bigger shredders in the decom facilities, and they are increasingly becoming harder to shred. Inside that shredded mix, you have neodymium magnets. This is market magnets in general. That's 90% owned by China. They've recently, as of the last week, put even more restrictions on the exports of these magnets. And magnets are critical to all aspects of our manufacturing and electronics, especially as we increasingly electrify. So there's a massive opportunity to create a higher precision demanufacturing process of these HDDs. And so we're building one. A 2-arm robot is not going to give you the throughput and the ultimate unit economics that make this viable. So we've had to build a custom lower mix, higher throughput machine, that project named Event Horizon, as we think about destroying that data. But we've given these systems lasers, cameras. They're going in, cutting into these hard drives, and then they're doing a high precision disassembly process. This is some of the older systems that we have that we can share kind of publicly. But these hard drives themselves are also going through their own technology innovation, that they're now helium-filled. Now, while the outside is still the same, they're increasingly denser, so there's more platters in them. Those things are breaking a lot of the shredders. And so a system like this, where we can deterministically demanufacture something to the level of material recovery that our customers need, is a really big win. So here we've gone through, we've taken off the lid, we've grabbed those precious magnets, and then here we go and take the PCBA off the back. It's always kind of a trade-off when we think about these dynamic processes, kind of speed versus the sortation of how we do the material. But ultimately, this machine kicks out about a hard drive a minute. So we do about 60 per hour on a given machine. So again, you kind of need fleets of these to meet the overall needs of the market. But that's why we build these as products that are deployable to our customers. So that kind of gives you a general sense here of how Moog thinks about circular manufacturing. We go with this demanufacturing perspective. We're doing the testing equipment, ultimately trying to create as much value that can be redeployed. And then we're even working on some of that manufacturing piece of how we bring what's harvested, mix it in on the manufacturing side, and redeploy that. Now, I think it's worth mentioning that automation in general here is expanding across the data center space. So there's some great work coming out of Meta in terms of how they're using mobile robots inside the DC to do asset tracking, identify errors, and provide more autonomy within inside the DC itself. Google has a similar program where they are working on hard drive swapping, and again, this is inside the data center. And so that is all reducing that need on the decom. So the more that we can do upstream of this process, the better. Now, it's worth noting we're producing, we're processing these millions of servers, which are creating tens of millions of components, and there's a need to track and trace this. Some, it's required through the security component, but also we want to keep track of what we're doing. How do we measure it? And there's this really big problem of creating a universal system that we can track and trace all of this stuff. So we've been working for the last 4 years on an open standard that I would love to engage the community on, but it is an ontology. That's just a fancy word for a formal representation of information. But it's about how we use identification, traceability, and marking and labeling of this so that we can track and trace all of this flowing from the manufacturing all the way through the demanufacturing, ultimately to the second lives. A quick example here is really just agreeing on some very, very basic things like universal IDs, UUIDs, and the format of those. We will have QPNs, MPNs, all the different kind of SKU names. We're looking to have a universally commodity so that we can create this interoperability between these systems. This is a realm that I've seen many people try and come and charge for, try and create businesses around this. It's a really hard thing because no one wants to pay for it. So let's all agree on kind of an open standard of how we exchange this information in a protected, private forward way, but it gives us the basic utility that we all require. And for the automation world, how we place a label, how we place a marking, how we know what that is hugely valuable in terms of what we can do with it and the amount of human effort that has to go into these processes. So we're contributing Origin Mark as this open standard. We've been working on this for a couple of years with a bunch of our industry partners. We have tens of thousands, if not more, assets with Origin Marks on them today. And we are working with OCP and iMason's Climate Accord to contribute this specification, that's the OCP language, around how we agree on some of these very basic data points within this standard so that we can all use this tool and not have to do as much Excel, spreadsheet, conversion, aliasing, all the things that are kind of slow, death by 1,000 cuts that, slow down some of these processes. So beyond automation, what's kind of next here? Well, we are working with companies like ABB, Dell, HP on redesigning the next generation of these products to be more automation and circular focused. So here you're seeing some of the work we've done with Dell on a project called Concept Luna. This is a laptop that's designed to be disassembled in less than 60 seconds by both people and robots. This can be upgradable. It's got no glues, screws, adhesives, and we've taken through many people the first time they've ever opened up a piece of electronics, and they've been able to do it more or less on the first try. I can do it, not to brag, in about 20 seconds. But it is really, really simple, and ultimately it's about how we use this design patterns that we're working on to define how things come together and come apart. So how do we process all these servers, all these hard drives? Well, we have these design patterns that we then couple up into assembly intelligence. Design patterns, in slightly more fancy words, it's software-defined, bidirectional kind of parametrics of how things come together and come apart. We have a whole catalog of them, and it's about turning those mechanical, electrical connections into these patterns. So walking through kind of that workflow quickly, this is server CAD, so we get the CAD of a server. We start mapping in the patterns themselves, and then we group all those patterns into what we call assembly intelligence, and then we can simulate the manufacturing and demanufacturing of that all kind of in real time. Now, additionally, we have some funding from the Department of Energy, where we're building out a tool chain so that this can live on top of your CAD software. So if you use Autodesk or SolidWorks, PCT, all of those things, it's about how we empower the designer to trade off those critical design decisions of, if I use a screw here, if I weld this, if I put a slide latch, what will that mean for ultimately my manufacturing, demanufacturing, and some of my circularity? And all of this is designed to work on top of our microfactory infrastructure. So I used to say, and I was very deliberate in that we didn't have a magic box. Our robots do not know how to take apart anything in the world. We have to tell them. We have to spend quite a lot of time here on what this is, give it all the identity, give it all this assembly intelligence. But in about the last 3 months, we've been working on some new technology here to try and create that magic box. So we are using CT X-ray scanners to create high-density 3D models of both internal and external at kind of a 25 micron level to then process a full three-dimensional model that then we can run through our processes to create these disassembly assembly processes, all kind of with AI-driven processing. So this is particularly cool because it goes through the whole process of matching up all those patterns, annotating it, and ultimately those things will be executed. We're not quite there yet. It's still going to take some time. But I think in terms of some of the big unlocks as we think about opening up the market further and further and what we can process, this is a very cool development. And so lastly, I kind of want to leave you with a more esoteric view on some of this. But it's, this was Richard Burdigan. He wrote a poem in 1967 called All Watched Over by Machines of Love and Grace. It kind of imagined technology as a partner, a guardian overlooking, all of us as we coexist in this natural world. Well, depending on how you read that, you can also see potentially he's making fun of us and our techno-optimism, and that technology and machines, even if they are full of grace and love, they're still machines. And so this can also paint a slightly bleak view where we're all watched over by machines of love and grace. Well, I've kind of come to believe that both readings of that poem have to be true. We need machines, but we also need them to be full of grace. And I think the true work is how, and the real work, the very urgent work, is how we make those things coexist today to build a machine not ruled by machines, but we use those machines to build the world that we want. That's all whatsoever by machines of love and grace. So I'll open it up for questions, and I really appreciate your time as we thought about automating, circularity, and the impacts that have on AI today. Thanks so much. I've been told that's the microphone to use if anyone has any questions.
Hi, thank you so much for that really interesting presentation. My name is Holly Elwood. I'm from the Global Electronics Council, and we run EPEAT, the Eco-Label for Sustainable Electronics. So would just love to have your thoughts on our new criteria that we just launched for circularity, and if you think it's hitting the mark in terms of helping to get the market where it needs to get to help enable the kind of work that you're trying to do, and what you would recommend in the future for us to make sure we keep that as cutting edge as possible, and what things do we need to look at trying to incorporate in the future that we don't have in there right now, because we want to be the tool that really purchasers can use to make this happen and to tell the market that they want more of this.
That's a great question, and thank you so much for your work. I think we hear a lot of fear within the OEMs, the people producing, especially in the electronic space, that they're going to be unfairly compared to one another. My apples are different than his oranges, and there's so much tension on how we standardize what the embodied carbon looks like when we design things. I think we can get there. I think LCAs, if you've ever gone through a life cycle assessment analysis, there's a lot of assumptions baked in. It's very static. It's very set to a specific moment in time. I think what we're trying to do with things like OriginMark and these other more dynamic systems is to harmonize the collection of that data so that we can have more real-time dynamic collections, so that we can create better estimates that can be measured against these regulations. I do think it's important that there's both a carrot and a stick in this market. Our customers don't always love to hear me say that. They're certainly not a fan of the stick, but you do see a lot of regulation coming out of, with the EPEAT, with the French Repairability Score Index. There's a lot of things that I think more or less are harmonized. There's some differences, but I think overall we're starting to come to a place where we can universally measure these things. It's going to take some time. I think a lot of people get caught up in the perfection of it all rather than the progress that's necessary. And ultimately, no product is going to be perfect. It's certainly not going to be perfect at the beginning. It's going to be a long journey. So the part that we'd like to work on with the community is how we provide those tools in that design process. When you think about the embodied carbon of a device, or the carbon generally, 80% of that or so is determined during the design phase. All of that happens in such a time-crunched space where a designer's typically just worried about getting the thing out, and is it manufacturable, and will I hit my mark, and will I do my design drop? And when you think about layering automation and circularity, the designer, the product designers, is typically struggling with the trade-off analysis. You go and you finish your design, and then someone says, well, what if it has half the screws? Well, okay, that's going to take me like another month to figure that out, and then I have no idea what the long-term impacts of that are. So we're trying to shorten the gap there between our design tools and the simulation and the manufacturing, so that we can do more of that real-time trade-off. Again, we ourselves have a lot of progress over perfection to do there in terms of how easy those tools are to use. But ultimately, we want to layer in the important work that you're doing from a regulation and kind of a standard setting into that work, so that you can see, okay, if I change my design like this, I reduce my assembly steps from 17 to 6 in the subassembly, that I'm going to meet this kind of score on these type of measurements. But ultimately, very much appreciate the work you're doing and see a lot of the great work. We're all kind of moving this together, and love to kind of connect further on how we can integrate those things more tightly.
Actually, I have so many questions. I don't even really know where to start. But one of the things that I think is I'd like to learn about is when we think about the vast expanse of devices that are out there is just nuts. And your examples pretty clearly look like, we're working on this OCP stuff. And so it reminds me of, the way IT Renew kind of came up into accepting truckloads of racks and decommissioning those things, right? And so, what does make sense to me is that there's the low-hanging fruit that has the highest potential, right? And with the OCP servers and all that stuff, highly standardized as opposed to all the junk you might get in a bunch of, EI 8310. So I guess my first question is really, when we look at all that, is there, that must take time to assess what do we want to automate, because the cost of automating it, I imagine, is rather high. And so how do you look at that and make those decisions? And then second to that is, what do you have in the market now? I think I interpreted from what you said that, right now we're able to decommission and, do all this magic stuff, which is so impressive, man, I'm telling you. Anyways, there was 2 or 3 questions in there.
Yeah, no, I appreciate that very much.
Remember them all.
No, thank you very much. So it is a really important aspect. So what we do a bunch of things that are on OCP. It's just we can't share it, as you can imagine. OCP is very generous in the way that we can share those designs, because you can go and download that CAD yourself today if you want. So I have no problem sharing it. Some of our other customers, not so much. When we decompose that server, we look at the patterns. So a DIMM slot is going to be more or less the same type of DIMM slot with a small variance across all the different servers. So that could be a ZT Systems, that could be a Foxconn server. Those individual components are actually quite standardized within themselves. They don't necessarily have the overall standardization of OCP and some of those larger mechanisms and how they work with racks. But when you get down into it, the patterns, a push press, a snap to connect, all of these patterns that we have are highly transferable across a wide range of products. I will say we were generally impressed we thought we had a much narrower scope of what we could automate, but as we kept feeding more systems in, kept doing more training, more pattern generation, more identification, we found our scope was much wider. And again, servers within that space are generally designed for some level of serviceability, which make it a much easier target. I will say it's a longer road to get into consumer electronics, things like cell phones, cheap $100 kind of full assemblies that are glued together. There's not a lot of hope in that current design that you're going to do anything other than material recovery. And there are companies like Apple that build robots that rip apart their iPhones. And that's because that's what you can really do with them. You cannot do a high precision repair process on an iPhone that's glued together. You can recycle the material and you can separate it in quite brutal ways. If you watch the videos, it feels like watching something you shouldn't be watching. But it's ultimately, because of that design dictates that disposition process. I would say in data centers and servers, there's a lot of hope here, and I think a lot of data we've already proven that we can go really, really wide across that process. The hyperscalers are unique in that their mix is, you can cover 17, 18 SKUs and cover quite a large percentage of their decommissioning mix in a given space. Kind of tier 3, tier 4, it does balloon out a lot. But then again, there's not actually that many server producers. So HPE, Dell, then kind of all of your Foxconn, all of that. That is still a highly kind of standardized design in general. So there's a lot of automation. One thing to note, the way that Moog charges for automation, to your point on ROI, is we actually sell as a service. So we do all the development of the automation processing, and then we deploy our machines, and we charge for every server that goes through the system. So we're very much tied as a partner with our customers to make sure those machines work and deliver them what they need to do, rather than saying, hey, here's a really shiny robot, have fun with it. So that is kind of the partnership model, and generally we like to think of the need for circularity requires and necessitates that partnership, because we're only a very, very thin slice in this much larger piece. So we can take something, turn it into all of its disparate parts, retest, but ultimately those parts need to go elsewhere in the chain. So kind of a rambling answer to your, I think, very good question. But having design patterns is really key, and we're finding those patterns match across a wide, wide variety of products. And our goal as a company is to enable circular manufacturing on all electronics. So we're starting in really high value, easy recovery, closer loop kind of supply chains. But as we bring down the cost of our technology and we increase its capability, we hope to get into that kind of middle tier consumer electronics market where a huge amount of that waste is. I think we're all guilty of having some devices in our bedside drawers. But we're looking to see how we can use some of those magic boxes to drive more recycling and more material recovery in that process. And then, I get emails from like vape manufacturers, right? So we see the full spectrum. I got an email for someone wanting us to disassemble underwear. I think there is like a floor of what I want to get personally involved in, but I think electronics is a good, we have a long way to go before we get full circularity there. So I appreciate your question.
I was going to say, your email's way too public then if you're getting those kinds of questions. Let me do a quick follow-up if you don't mind. So it sounds to me like it's primarily customer-driven, right? And that makes complete sense. There's these great big companies that have all this stuff. The good news for you is that the, useful life of servers is growing, so that makes it a little bit better. But there's a set of economics into what you're doing, I'm sure. And so a customer comes to you and they say, I have this. I mean, there must be an analysis process where you go through and say, this is worth it, and these aren't, unfortunately.
Yeah, I think that's great. So I think we do that all the time. It's well analyzed. So where we find where it doesn't cross the economic threshold, typically we find there's a redesign path to say, okay, when's the best time to plant a tree? 20 years ago, and that we would have loved to redesign your product 20 years ago, so we would be dealing with a serviceable product now. But we're not. So how do we start on your next generation of products? So when this comes end of life in 7 years, it's highly economic, highly scalable, highly profitable for you. And so that's typically where we see that mix break. So if something is ultimately not going to, because of how it's designed or its collection process, isn't going to be able to return an economic return, we say, let's focus on a redesign on that next generation version. Now, again, my goal is still to bring the capability and the cost down on the capability up and the cost down so that we can do all those things, at least for recycling. And ultimately, how do we offset the profit that we're making here to do kind of non-profitable recycling activities just so that we can keep that material flowing through and not ending up in a landfill. But we have a long way to go before we can really do that at the scale that we want to.
Well, you guys are doing amazing work, and I can tell from your passion, you're probably heartbroken all the time of all the stuff you can't do just yet. Anyways, nice work.
I appreciate it. Thank you. All right. Anybody else? Any other questions? All right. Well, thank you very much. I appreciate all your time.